Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome back to this lecture, and we will continue our discussion on the creep deformation. In the last class we looked at the introduction to this creep and the type of creep curve, the various stages of the creep curve and so on, right? And today's class we will discuss very specifically the important mechanisms. There are several mechanisms being reported in the literature depending upon the material and the state of stress and the strain rate, temperature combinations. Okay, because we have already seen that the creep deformation is a strong function of these parameters, right? So some of the prominent mechanisms we will go through and then see how we can comprehend the idea of the creep deformation in the very variety of material. So depending on the temperature and applied stress, dislocation glide, dislocation climb, or diffusional creep flow mechanisms may dominate creep deformation. This is very important. Okay, so it is not just one particular mechanism we are going to say that this is the mechanisms, because as you rightly see that this deformation highly depend on the applied stress and the dislocation climb or glide or diffusional mechanisms. So what is the plot shown here? It is the activation energy for self-diffusion, which is kilojoule per mole, and activation energy for the high temperature creep, which is kilojoule per mole. What is given? So the high temperature activation energy correlate closely with self-diffusion activation energy. So this is one proof that the self-diffusion activation energy is correlating very well with the high temperature creep. So this correlation indicates that creep deformation is associated with diffusional flow. So this is one experimental evidence clearly shows that high temperature deformation creep involves diffusional flow. So now that was kind of a proof, but then we will see what kind of stress and temperature combination dictates what kind of creep mechanisms dominates. We can look at like that. For in that case, we will first look at what is the dislocation glide at low temperature, relatively low temperature. So what you see here in the plot is very a simple one, energy versus position, where the dislocation approaches the plane, swift plane, and this is an obstacle as a plane. So this is a barrier. U0 is the activation barrier where the dislocation has to cross through. So normally we have, if you recall, we have just looked at this exactly similar approach of thermally activation process. Two times, in fact, we have seen. One, we have just seen that at how the thermal energy KT assists the dislocation to cross the barrier. Okay. Otherwise, whether the thermal activation alone has to do the job or the applied stress has to do the job. So this is a kind of an activation barrier. How the applied stress is going to aid this or modify this profile. This is what we are going to see. A schematic of energy variation with the dislocation position as dislocation approaches slip plane obstacle. And what is shown in B, suppose if the applied shear stress is greater than 0, then what happens is it just alters this profile. This the energy required to cross this barrier is altered. What does this show? Delta U is an applied stress, so that means it reduces the barrier. That means it assists the energy barrier, which normally accommodated or circumvented by the thermal fluctuation. So it applied stress, it reduces that energy requirement. So that's what's shown here. The part of the work, that is delta U is required to overcome the barrier U naught is provided by the applied stress, that is tau applied here, and the remainder by thermal energy, that is kT. The dislocation glide creep rate can be deduced from the kinetic principles as discussed in the text, what we are going to see. So the activation energy U naught is the integral of the force distance curve. So this is integral. This already we have seen this. We have enough background to understand this, which is up to the position x is equal to 0 and represents the energy required for a dislocation to bypass the obstacle. Such an energy can be supplied thermally. The magnitude of the thermal energy is in the order of kT. An applied stress tends to drive the dislocation past the barrier and alters the energy obstacle and energy distance profile, which is shown in this figure. Now the dislocation is in the lower energy state after passing the obstacle. So you can see that now the dislocation energy is lower as compared to the before it crossing the obstacle. The energy difference is noted as delta U, and the principles of kinetics allows determination of the creep rate. So how do we find the creep rate for the dislocation glide creep? The rate at which the dislocation bypass the obstacle in the forward, that is stress aided direction, is given by forward rate is approximately equal to exponential times minus U naught by delta U by kT. This is for the forward rate. Likewise, the reverse reaction rate, that is the dislocation can move in the direction opposite to the favored by the applied stress, but at a less rate, is proportional to exponential minus U naught by kT. So what we require is a net rate. So the net rate, which is proportional to the strain rate, scales with the difference between these terms. So what is the difference? Thus the dislocation glide creep rate, that is epsilon dot dg. Dg stand for dislocation glide, can be written like this. So epsilon dot dg is equal to epsilon dot naught exponential into minus U naught by kT into exponential delta U by kT minus 1. At low temperatures of concern, exponential del U by kT is much greater than unity, except at very low stress levels. We can rewrite this expression like this: epsilon dot dg is approximately equal to epsilon dot naught times exponential minus delta U naught by kT into exponential delta U by kT. So this can be written like this after we modify this exponential term. Epsilon dot 0 is a material parameter relating to the frequency of atomic vibrations and has a units of per second. So this is a material parameter. The energy delta U is related to and increases with the applied stress. Example, delta U is equal to 0 if tau is equal to 0. In essence, delta U is the work done by the stress in approaching the obstacle, and this work reduces the thermal energy required to overcome the barrier. This we have already stated. If L is the effective spacing between the slip plane obstacles, then delta U is equal to integral L times tau B dx, where the integral is taken from x is equal to infinity to position at which tau B, which is equal to F applied. So this equation, they are all very familiar to you. We have already looked at it, right? When we looked at the dislocation dynamics also, we have seen that force, right? Where the B is a Burgess vector, this is a stress. So the force required, right? So we have seen that. So this is also the similar expression. So you know the L is the length, effective spacing between the slip plane obstacles, and then it gives a kind of energy term, right? The integral can be approximated as B tau AS, where AS is an approximate area on the slip plane. On doing so, the strain rate is obtained as epsilon dot dg is equal to epsilon dot naught into exponential minus U naught by kT into exponential tau b as by kT. So what is this? This term we know, this is an energy barrier, but this one is the complete again an energy. So this is a stress into area. So it is at volume. So stress into volume term it comes, right? So this is a ratio of stress into volume divided by the thermal energy term. So this term will keep on repeating in this different kind of mechanisms if you just keep a track of this. Although the above equation is derived on a model for which plastic strain does not devolve on atomic diffusion, it bears similarity to creep equations involving such diffusion. In particular, the creep rate is controlled by an intrinsic activation energy, that is U0 in the equation. Moreover, the rate depends also on the ratio of stress assisted energy. So that is what I just mentioned. Tau b as is nothing but the volume into stress to thermal energy. So stress assisted energy to thermal energy. It's a ratio. So this ratio is, it is an additional term. Additional term comes along with the intrinsic activation energy. That's what it says. So the creep rate depends upon the ratio of stress assisted energy to thermal energy. The numerator in this ratio has a dimension of energy, and it can be viewed as a product of stress and volume. So this is stress tau, and then BAS is a volume. So now that is about the dislocation glide creep. That's a creep rate. If it is completely controlled by dislocation glide, that is relatively low temperatures, high stress. Okay, so that is how we should do it. Now we look at diffusion flow creep mechanism. A popular one is Nabarro Herring Creep. So now we have to reverse the situation. Slightly high temperature, low stress. So high stress, low temperature. Now it is reversed. High temperature, low stress. Nabarro Herring Creep is accompanied solely by diffusional mass transport. And NH creep dominates creep behavior at much lower stress levels and higher temperatures than those at which creep is controlled solely by the dislocation glide. Since it does not involve dislocations, Nabarro Herring creep is also observed in amorphous materials. So this is one advantage. Since there is no dislocation activity, this kind of formulation can be applied to amorphous materials also. But we will now just look at the crystalline material context. Right? So what is the model? So here is the model where you can consider a square type of a single crystal, and which is being subjected to biaxial loading. One is tension, other is compression, and the crystal width is D. And then you can see the diffusion flux, how it goes with respect in response to the stress and the temperature. So that is what it is given. So we will now describe the grain illustrated in figure may be considered either an isolated single crystal or an individual grain within a polycrystal. So both are possible. As indicated, the lateral sides of the crystal are subjected to a compressive stress, and the horizontal sides to a tensile stress. So, since it is a diffusional flow, Nabarro Herring Creep results from a higher vacancy concentration in the regions of a material experiencing a tensile stress compared to those subjected to compressive stress. This results in the vacancy flux from the former to the later region, that is a tensile region to a compression region, and a mass flux in the opposite direction. That is what is shown here. Okay. So vacancy flux is one direction, mass flux is the opposite direction. So you can see that dotted line and the solid line, right? So that's what it's shown here. This results in the vacancy flux from the former, that is from the tensile to compression region, and the later, that is the mass flux, is going from sides to compression to tensile region. So this is what you have to appreciate. The resulting change in the grain dimension is shown in the B, is equivalent to the creep strength. So the resulting shape change. So the original shape is there. This is an after flux. So this change is the creep strength. The change in length, delta D. So the D, this is D. So this is delta D of the crystal along the tensile axis is related to dV. This is volume, delta V. By delta V is approximately equal to D square times delta D. So this is a change in volume because of this diffusion flux is given by this expression. The stresses alter the atomic volume in this region. It is increased in the regions experiencing tensile stress and decreased in the volume under the compression. So this we have seen in the schematic. As a result, the activation energy for vacancy formation is altered by plus or minus sigma omega, where omega is the atomic volume and plus or minus signs refers to compressive and tensile regions respectively. Okay, so now we are talking about the activation energy for the vacancy formation by the factor sigma times volume. So always we are looking at the microstructural dimensions here. Okay, so stress into volume. Even in the previous case, we looked at stress into volume term, right? Thus, the fractional vacancy concentration in the tensile and compressively stressed region are given by NV, that is fraction of vacancy in the tension is approximately equal to exponential minus QF by KT into exponential sigma omega by KT. So it's the same type of expressions we will get. And in compression, NV is equal to exponential minus QF by KT into exponential minus sigma omega by KT. The minus sign is because of the compression here, just to make a difference between these two. Where QF is the vacancy formation energy, provided the grain boundary is an excellent source or sink for vacancies, the grain in the figure. If you can see that figure, it's a polycrystal. If you consider that figure as a polycrystal, then the grain boundary can act as a sink. This is a well-known fact. Or if it is single crystal, the surface of it behaves likewise. So there are two things. If you consider as a single crystal, then the surface of the single crystal will act as a boundary. And if it is a polycrystal, then you can look at any boundary which will act as a sink for vacancies. The vacancy concentration given by the equation are always maintained at horizontal and lateral surfaces. Okay. The different concentrations there drive a net flux of vacancies from the tensile to compressively stressed region, and this is equal to a net mass flux in the opposite direction. That's what the schematic also shows with the dotted arrow and the solid arrow. Yeah, as illustrated in figure, this produces a change in the grain shape. The grain elongates in one direction and contracts in the other. That is, creep deformation occurs. The creep rate resulting from this process is estimated as follows. The vacancy flux JV through the crystal is given by JV is equal to minus dV times dou NV by dou X. There is a typo here. This is not subscript X. This is a dou X. Where dV is the vacancy diffusivity, which is equal to d naught V into exponential minus Qm by Kt, where Qm is the vacancy motion energy and dou NV by dou X is the vacancy concentration gradient. This you are familiar with this, right? We have seen this gradient in several occasions in the previous discussion, right? So here it is a vacancy concentration gradient. The term delta x can be taken as a characteristic diffusion distance proportional to the grain size. Very important idea. So the delta x here is considered as a grain size d. Okay, whereas delta NV is the difference between the equations. So what we have given two compression and tension directions, we have given a vacancy concentration. The difference is taken as delta NV. Multiplication of the equation by the diffusion area, that is proportional to d square, gives the volumetric flow rate. What is volumetric flow rate? Delta V by delta T. Okay, so the vacancy flux is now equated to volumetric flow rate. It represents the volume transferred per unit time. Okay, that is dou V by dou T from the lateral to the top and bottom sides of the crystal. So according to the above reasoning, we can write the expression like this: dou V by dou T, that is volume transferred per unit time, which is equal to D naught V times D into exponential minus QF plus QM by KT into exponential sigma omega by KT minus exponential minus sigma omega by KT. So this expression we are simply substituting from the previous equations. You don't get confused that the equation is becoming bigger. We have just seen one by one, then we are now putting everything together. So nothing is new here. All the terms we have discussed, right? All the terms we have discussed. The corresponding Nabarro Herring Creep rate, that is epsilon dot NH, is expressed as 1 by D into delta D by delta T. Thus can be written as epsilon dot NH is equal to D naught V by D square times exponential minus QF plus QM by KT into exponential minus sigma omega by KT minus exponential minus sigma omega by KT. So it's the same equation. So this is a creep rate, Nabarro Herring creep rate. The term D naught V exponential minus QF plus QM by KT is identically equal to the lattice self-diffusion coefficient DL. So this can be just replaced by this. Moreover, at high temperatures and low stresses, at which Nabarro Herring creep is important, sigma omega is always less than the KT. That means the stress assisted energy is significantly smaller than the thermal energy. That is how you have to read this, right? We have just talked about it. So that the exponential plus or minus sigma omega by KT can be written like this: 1 plus or minus sigma omega by KT. So this is very simple idea. Using these relations and letting a constant A and H represent the geometrical factors that we did not fully consider, epsilon dot NH can be rewritten as epsilon dot NH is equal to A and H dl by d square into sigma omega by KT. So this is a final expression for this Nabarro Herring creep. As mentioned, Nabarro Herring creep is important at high temperatures and low stresses. That is, in the temperature stress regime where the dislocation glide is not important. Very important point to note also. Nabarro Herring is more important in creep of ceramics than in metals, because ceramics, they deform only at very high temperatures, right? So that's where it is important. This is so because dislocation mechanisms of creep can be considered competitive with Nabarro Herring creep, and dislocation motion is generally more difficult to effect in ceramics than in metals. This aspect also we know. Dislocation activity is very limited. Okay, we have discussed that aspect several times. So the next is Coble Creep. Coble Creep is closely related to Nabarro Herring Creep. For example, Coble Creep is driven by the same vacancy concentration gradient. Okay, so that is uh, dou NV by dou T, that is vacancy concentration gradient, right? So then what is the difference? However, in Coble Creep, mass transport occurs by diffusion along grain boundaries. Very important point to note. We are looking at only the grain boundary here in the polycrystal or along the surface of the single crystal. So we are not, the lattice diffusion is not considered here, but the diffusion along the grain boundary is only considered. That is how you should look at it. For a polycrystal, the diffusion area is thus proportional to delta prime D, where delta prime is an effective grain boundary thickness for mass transport. Analysis similar to that employed in Nabarro Herring Creep yields an expression for Coble Creep like this, in this form, which is epsilon dot C. C stands for Coble, which is equal to AC into dGB into delta prime by d cube into sigma omega by kt. So what is the difference, primary difference here? We will see one by one. In the above equation, QF represents as it did previously and the vacancy formation energy, but QM is the activation energy for the atomic motion along the grain boundary. So the motion is the lattice motion previous case, but here it is motion along the grain boundary. The exponentials containing these terms have been incorporated into dGB. All the exponential terms have absorbed into this constant, dGB parameter, which represents the effective grain boundary diffusivity or surface diffusivity as the crystal is concerned. As indicated by the above equation, Coble Creep is more sensitive to grain size than Nabarro Herring Creep. How are we saying this? You can see that it is a d cube term is here, right? So it is very important for the fine grained material. Thus, even though both forms of creep are favored by high temperature and low stress, Coble Creep will be more important in very fine grained material. So this is a very perceptible, observation. D cube, the creep rate is inversely proportional to d cube. So that means it is very much dependent on the grain size. So now we'll see some schematic which will explain this Coble Creep much more effectively. What is shown here? These are all the grains and which are subjected to high temperature deformation. You are seeing that XZ, XYZ, that line, we are going to trace it as the deformation proceeds. Okay. You just look at this triple junction A, B, C, D. There are 4 triple junctions we are going to trace as the deformation proceeds. That's why it is marked here. So grain 1, 2, 3, 4. After a deformation, what happens? First, we'll read this caption. 4 grains in a 2-dimensional hexagonal array before creep deformation. Following the diffusional creep, one dimension of the grain is increased and the other decreased and voids form between the grains. Suppose you assume that you are pulling this the tensile direction, then what happens? All this grain will try to elongate in this tensile axis. Then because of that, what happens? The voids are getting created here. So how this is getting accommodated during the creep deformation? If voids are happening immediately, then the material will fail, right? The creep deformation will result in the fracture, because in creep deformation we are just measuring only the strain, not the fracture time, right? So how the deformation is proceed with this, how this the void formation is compensated, how it is accommodated, that is what is shown here. So what is shown here? The voids are removed by grain boundary sliding. we are introducing a term here, grain boundary sliding. That means this grain 2 slides towards, this point, the junction B, and the grain 1 is also trying to slide towards junction B. So that's why you can see that there is a breakage in the XY Z line. It becomes X Y dash and Y dash Y double dash Z. So it got split. That means the grain 1 has just slide through this boundary and reach the point B. That B becomes B dash now, and A becomes A dash now. Similarly, this 4, grain 4 and grain 3, they're also sliding along this grain boundary. So then it becomes homogeneous. So how do we understand this? The extent of sliding is quantified by the distance y double prime. Where is that? Y double prime now gives the sliding distance. How much the because it is a homogeneous deformation, each grain will slide the similar distance, right? Which is an offset along the boundary between grain 1 and 3 of the original vertical scribe line X, Y, Z. So how do we understand this? To prevent the formation of internal voids or cracks during polycrystalline diffusional creep, additional mass transfer must occur at the grain boundaries. Obviously, right, if you want to avoid the voids or a crack, how to fill? Unless the diffusional flow happens, this cannot be filled. This results in grain boundary sliding and diffusional creep. Diffusional creep rate must be balanced exactly by the grain boundary sliding rate if the internal voids are not to. So this is a dynamical process. It's not just it has to take in place quickly to avoid the void formation, right? So it has to balance. These two rates has to balance with each other. The situation is illustrated in the figure, the previous figure, for several grains within a polycrystal. As shown, unaccommodated creep leads to grain boundary separation. So this is what the figure B, that is where the voids and cracks forms along the boundary. That is called unaccommodated creep. The separation is prevented by concurrent displacement of grains via their sliding over one another so as to heal the cracks. So it's kind of a nice description we are giving. Healing the cracks that would be formed by unaccommodated diffusional flow. Diffusional flow and grain boundary sliding, therefore, can be considered as sequential processes. The first diffusional flow causes the elongation and void formation, and the subsequent grain boundary sliding heals it. So there is no void formation prevails after this. This is what it means. In which mass is first transported by Nabarro Herring Creep and or Coble Creep, and a grain shape change and a separation are effected. So these are all the sequence of events. This is followed by crack healing via grain boundary sliding. Since the grain boundary sliding and the diffusional flow process occur sequentially, the net creep rate is lesser of the separate creep rates. So this is quite understandable, right? The net creep rate is considering all this activity, Nabarro Herring, Coble Creep, and then grain boundary sliding. All these events has to be taken into account. So that is why it is called a net creep rate, which is lesser than the individual creep rate. So depending upon the stress and local stress and the temperature and other factors, so many other factors, each mechanisms of the creep can dominate, and the net one is much less than the individual events. That's what it is.